So good afternoon. My name is Divya OBEROI. I am from National Center for Radio Astrophysics right here in the Pune University campus. And I believe you're all students of the astrostatistics course, right? And what I've been asked to do is to give you a real life example of application of one of the techniques which you have studied, which is Gaussian mixture modeling, to a really frontline research area, which is where I happen to be working. This was work of Rohit Sharma, who was or part of thesis work of Rohit Sharma, who was a PhD student at NCRA, who was submitted his thesis only earlier this year, and Mihir was our collaborator. Okay, so I'll start by giving you a little bit of introduction to the Sun and the Coronal, because I'm not sure of the astronomy or the background you might have about the Sun. So to put the problem in context, I'll start by telling you something about the Sun and the Coronal, and then about the instrument from which we use the data so that you understand what we are dealing with. I also need to tell you something about a very vexing problem which people have been dealing with for a very long time now. It's called the coronal heating problem, and what are the possible ways people are thinking of resolving that problem. And all of these things will form the background for what I want to tell you, which is about a Gaussian mixtures based approach towards investigating this problem and what it led to. And at the end, I have an ad for a different project, which I'll have a few slides on. And so please feel free to interrupt me to ask any questions whenever you have them. If I think it will be a long detour to answer that, then I'll take it at the end. But that should not restrict you from asking any questions whenever you have them. Okay? Okay. So let's start with just some vital statistics of the Sun, right, to get a sense for the scale of the object you are dealing with. So let's talk in terms of the size of the Earth. The size of the Sun is roughly 100 times that of the Earth. Okay? It also so happens that the mass of the Sun is about 1,000,000 times that of the Earth, which right away tells you that the average density of these objects must be very similar. The distance between the Earth and the Sun is about 150 million kilometers. It takes light almost 8 minutes to travel from the Sun to the Earth. If you measure it in units of size of the Sun itself, it's about 214 solar radii, right? So that's how it is. The emission from the Sun is a black body emission, or can be modeled reasonably well as a black body emission. If you were to do that, then it turns out to be a black body corresponding to a temperature of 5,800 Kelvin. How many of you don't have physics background? Okay, quite a few of you. So, do you know what a black body is? Yeah. Yes? No? For the ones who don't have physics background, do you know what a black body is? Yeah. It's when you have emission, which is determined purely just by the temperature of that object and the size of that object. That emission has a particular shape, spectral shape, and that is governed just by one number. That's the temperature of the body. That shape of that spectrum is called the Planck spectrum. And I won't go into any more details about what a black body is, but essentially if you heat something up, take something which is really black and just keep heating it up, the radiation you get from that keeps changing, and it depends only on the temperature of that. And just by knowing the temperature, I can predict the radiation I am getting at any frequency. And even the coldest object emits at the entire spectral band, and so does the hottest object. Okay? It so happens for our Sun, the yellow disk which you see, its temperature corresponds to something like 5,800 Kelvin. Kelvin is of course a unit to measure the temperature of the Sun, and 0 degree centigrade is equal to 273 Kelvin. Okay? The luminosity of the Sun, which is basically the total amount of power which is radiated out by the Sun, integrated over all the spectrum, all the wavelengths in the electromagnetic spectrum, is about this much, 10 to the 26 watts. Okay. What is more interesting is something which is called the solar constant. That is the amount of energy which is incident at the top of the Earth's atmosphere, right? So if you take 1 meter squared area, it is getting something like 1.4 kilowatts of energy from the Sun, right? A kilowatt is, your microwave is typically a kilowatt. your washing machine can be about 2 kilowatts or something like that. It's a pretty large amount of energy. So if we can just figure out how to harness a lot of this energy incident on our Earth's atmosphere, we have a solution, or we can find a solution to our energy generation problems. The sun is about a middle-aged star. It's already lived for about 5 billion years, another 4.5 billion years or so to go, so we don't have to worry about the sun going anywhere. Okay, taking a look inside the sun, at the very center of the sun is where these nuclear reactions take place. The temperature there is unimaginably high. It's something like 14 million Kelvin. Right, that is where hydrogen nuclei are fusing to form helium, and the slight difference in mass between the helium atom and the two hydrogen atoms which combine to form that gives rise to the energy which is eventually coming out from the sun. So right on top of this thermonuclear zone sits something called the radiative zone. It's called the radiative zone because the most efficient mechanism for transport of energy in that region is radiation. Right? And even though it is most efficient, the photon which is released at the top of the thermonuclear zone is scattered many times, and it takes it almost 1 million years to random walk its way from top of this layer to the bottom of the next layer, which is called the convective zone. That is called the convective zone because by then the material has cooled enough that it can now absorb this photon and keep that energy with itself as heat. And as it heats up, it is the bottom layer of this convective zone which is heating up, and that is because it is the bottom layer of the liquid which has become hotter now, it is going to give rise to convection. And that is where these convective cells are set up, and they are sort of in various layers. So at the bottom there is the layer with the largest cell size, and as you go to higher heights, there are convective cells which are smaller in size which are set up. Okay. And on the surface of the sun, we see a whole lot of features. The most prominent, I'll get to the surface features in a minute. There is something which was not evident at all in the previous picture, which is what I'm trying to highlight here. This is a picture of a sun taken during a total solar eclipse. Okay. And just to make it look pretty, what they did is that they took a picture of the sun in H-alpha band right after the eclipse and then planted that in the center. Just so that you don't have a big black hole at the center, you have the sun at the center. If you look at this picture, what does it remind you of? And feel free to, don't be afraid of just making your guess. Whatever comes to your mind, just tell me. What does this pattern which you see outside the sun remind you of? Magnetic fields, right? But we can't see magnetic fields. So how come these magnetic fields are so evident in this picture? Any guesses here? Right, so you probably had played with iron filings and a bar magnet at some point, and you sprinkle the filings and tap the paper, and the magnetic lines of field reveal themselves to you, right? Something similar is happening here, except what you are seeing here is the light scattered from the electrons which are there in the corona. Okay? This light is of course there all the time, except that this light is so much fainter than what is coming from the sun itself that we are not able to see it. It's just the same reason as why you can't see stars during the day. Of course they are there, right? Yeah. So this light is really faint. It's a tiny fraction of what is being radiated by the sun. And what this tells you is that not only there is this magnetic field, not only there is this plasma which is filling up all this region around the sun, this plasma is being controlled by the magnetic field. That is why this plasma has arranged itself exactly along the lines of this magnetic field, just like those iron filings, right, which got arranged exactly according to your magnetic field. So what this is telling you, that it is the energy in the magnetic field which is by far dominating the energy, the kinetic energy in the plasma. Okay. Such a medium where there's a quantity which plasma physicists like to define, it's called beta. It is the ratio of the kinetic energy of the plasma to the magnetic energy in there, magnetic energy in the medium. And in this case, in this low corona, it's a low beta medium. Okay? So the basic point is that it is the magnetic field which is going to call the shots. That is going to dominate everything which is happening here. Okay, so these I showed you these magnetic fields. Here is another way to look at them. If I just look at closely at some place on the sun, these are the convective cells which I am talking about. And this region is also actually full of magnetic field, and from somewhere beneath the convective cells, there appears a strand or I don't know, a rope of magnetic field, and it erupts through the surface. And this is actually what it looks like. Okay. So these sunspots or active regions, this image, by the way, was taken in white light from a satellite by the name Hinode. SOT is just Solar Optical Telescope. It's one of the payloads on top of that satellite. This is a very high resolution image of the sun. The small granules you see here, these are the so-called supergranular convection cells. Okay. If this was a movie, you would see them sort of bubbling, moving slightly. Okay. These are the regions from where this magnetic field is erupting, and because magnetic field is always continuous, it's like a thread with no end, right? So just as much of the magnetic field is coming out of the surface also has to go into the surface. So these sunspots or these active regions, they always appear in pairs. And if I had an instrument which would show me the polarity of this magnetic field, I would typically find that there is a positive. Positive polarity is typically defined as when the field is coming towards you or coming outside the surface of the sun, and the other one would be negative. They don't have to have the same area because magnetic field can be compressed. The amount of magnetic flux which is coming out and going in has to be the same, but it need not be confined into exactly the same area. These are the places where the magnetic flux is almost perpendicular to the surface. This so-called, so this is called the umbra and this is called the penumbra, just because this is dark and this is light, and people were making an analogy with sunspots, with the eclipses. This is this sort of fainter region where you can also see a lot of striations sort of coming out of the sun. This is the region where the field has a larger non-radial component. So the field is sort of coming out and flaring up. Okay. That is what it appears like. Okay. And just to give you the picture again, this part is going straight up. There is a lot of other magnetic field which is actually just flaring out from there, which is also there. The reason why these things appear as dark spots is because when these strong magnetic fields are present, the convection, which is responsible for bringing the hot plasma up from the bottom to the top, gets inhibited. That is why it appears cooler as compared to its surroundings, and the temperatures here can be order 4000 to 5000 Kelvin, okay, as compared to 6000, 5800 Kelvin in this region. Okay. And of course, if you were to look at the same thing in a different using different electromagnetic radiation, different waveband, this was white light. This is, on the other hand, 171 angstrom, which corresponds to I think something like a large fraction of a million Kelvin in terms of the temperature of that radiation. You can see structures similar to what you were seeing here, right? If you take a look at these things, and you can imagine something very similar is taking place here. So this is again these magnetic fields which are confining very hot plasma, right? So now you have a bunch of questions to answer. First of all, something has to heat up this plasma. The surface of the sun, we said, was 5800 Kelvin. This, I said, is approaching a million Kelvin, right? So something has to now heat up this plasma to such high temperatures, and then it also needs to have sufficient magnetic field, magnetic pressure, let's say, to be able to confine this very hot plasma into these very well defined channels. Okay? And that's something we'll come back to as we go, as we progress in my talk. Okay. So something more about this, the structure of the corona. So for the bulk of what I am interested in, it is the corona which we will be dealing with, right? What is happening on the surface and beyond. That is the region of my interest. So, sorry, starting from the surface of the sun, the visible surface of the sun, which is called the photosphere. Here is the height measured from the photosphere in units of kilometers on a log scale. On the y-axis, there are two curves. There is one showing the temperature, which is the solid curve, and this dashed curve shows you the density. Okay. So let's look at the temperature curve first. So what it shows that there is a region, actually quite a small region, order 1000 kilometers or so, on the surface of the sun, which is called the chromosphere. Okay. where the temperature is dropping slightly, and then you encounter a region called the transition region, which is actually amazingly thin, which is just a few hundred kilometers. And within these few hundred kilometers, this temperature jumps by almost 2 orders of magnitude. From something like 10 to the power 4 Kelvin, it jumps to something like 10 to the power 6 Kelvin, right? A million Kelvin. Okay? That is really strange, okay? Because I'll be talking a little bit more about it a little further down, so let me not say too much more about it right now. And what is happening to the density? Well, the density is going the other way. The density is much, much higher as you are close to the sun. In this region, it is actually falling much, much steeper than 1 upon r squared. It is falling, the polynomial people usually use to model this. The dominant term is 1 upon r to the power 6, and it has another term which is r to the power 12. So it's dropping very, very steeply. The density of the coronal medium is dropping very steeply. After a little bit further down than this, it begins to drop off as 1 upon r squared. Okay? And why this steep drop is there is, this means that okay, there is something which is flowing out from the sun. Not only it is flowing out, it is also being accelerated. Right? If it was something which was just coasting along, just moving with a constant velocity, it would fall off as 1 upon r squared. If I have to make it fall much faster than that, that means that I must accelerate this thing. Right? That's again something which I'll touch upon as we go. And just to remind you, this region is full of magnetic fields. Okay? So these magnetic fields are going to play a very important role in whatever is happening in this corona. Okay?
So
yeah.
This distance scale is starting from the surface of the sun.
Correct. Yeah.
Up to the height scale.
Yes. Yeah. Okay. Okay. So another sort of pictorial view of the sun at many different wavelengths. If you were to look at, say, something like this, okay, the credits first. All of these images are from a satellite by the name Solar Dynamics Observatory, which was launched by NASA quite a few years ago now. And the beauty of this thing is that it gives you all of these images, right? There's some 13 images there in different wavebands simultaneously or near simultaneously. So you can see a lot of things changing, how the evolution is taking place in an unprecedented detail as compared to what was possible earlier. This is the one which is closest to what we see with our eyes. Okay? So that looks sort of familiar. The center is darker, brighter, the limb is darker, you can see the active regions, and that's what you sort of expect. This is something called a magnetogram, which is showing you the presence of concentrations of magnetic fields. So wherever it is dark, the magnetic field is going in, wherever it is bright, the magnetic field is coming out. And you can see roughly in the vicinity of the regions of these sunspots or active regions is where you see some structure. And a dark region is always accompanied by a bright region next to it. It may not be the same size, it may not be the same shade of brightness or darkness, but whenever people have tried to do this sort of flux conservation, they found that to the ability of the instrument, right, to the error bar associated with your measurement, this flux has been conserved. Okay. Then starting from here to here are various wavelengths of light, electromagnetic radiation, which are probing plasma at some particular temperature. And they are starting at something like 4,500 Kelvin, which is the temperature of the sunspots, roughly around there. And they are going all the way up to around 10 million Kelvin, which is very, very hot plasma, right? And as you proceed along this, you see that somewhere around here, which is this 193 angstrom, which I think was, earlier image I was showing you was 171 angstrom, which was at about 0.6 million Kelvin. You see that there is some change which you can notice as you go from here. One of the changes I want to point out is that roughly till here, the disk of the sun was a well-defined disk. You could draw a line with your pencil and say that sun is inside this, and outside this there is no sun. By the time you are sitting here at a million Kelvin, you see that there is a fuzz which is there around the disk of the sun, right? That there is a lot of medium which has been heated to this million Kelvin, which you can begin to see. And that continues till about here and then begins to reduce a little bit by the time you are at 10 million Kelvin. Okay? If you were to again look for where these bright regions are present, you will find a very strong correlation between where these active regions are present. Now remember, the active regions are the regions which also have the strongest magnetic fields, right? So it is the places which have the strongest magnetic fields which also tend to have the hottest plasma. The places, okay, you can't see it in this image because it is too, it doesn't have enough resolution or scale, but you could see it in earlier images like this, that even when you are seeing the hotter plasma, it is always confined by this magnetic field, or it is always tracing out things which suggest magnetic field. Some of these would be open lines of field, but there will be many which will be closed as well, right? So again, magnetic fields are the key, okay? And it shows you that these places are capable of heating plasma all the way up to tens of millions of Kelvin, okay? Okay. Now, sorry, just a moment. Yeah. Okay, something a bit a different aspect of the sun. There is something called the solar cycle, which probably many of you are already aware of, right? Because sun was the brightest source in the sky and very important in many cultures. A lot of people had already been observing the sun, even though we did not at that time have much of a scientific understanding of what that object is. And so on the x-axis here is time in years and months. The first number there is 1749 July, right? Since starting from around there, we have accurate records of how many sunspots were there on the sun. Okay, so it's among the longest time series where we have good accurate data of some astronomical measurement. And so people had been doing it, and they found something quite interesting. They found that, well, it's a number which grows and then comes down and grows again and comes down again. It does not always come to the same level, does not always drop to the same level either, right? So if you were to look at the distance between the maximas or minimas, you find numbers ranging between 9 years and 14 years. So the consecutive maxima or consecutive minima, the separation between them ranges between 9 and 14. If you were to look at the average over many solar cycles, it's around 11. That is the standard accepted number. 11 years is the length of the solar cycle. Okay, if you were to, okay, these numbers are monthly smoothed sunspot numbers. Actually, it so happens that the sunspot number can change quite significantly over short term time scales. So a sunspot might live just for 2 or 3 days, and it might disappear, right? So if you were to take daily measurements and plot them, you get something which is much more jagged. But if you smooth it over a longer term, you have, of course, a nicer, smoother curve which appears. This one, and from the time they started, people have been giving them numbers. So right now we are coming to the end of cycle 24. Okay? And this shows the past 3 cycles, and it shows that the maxima has been progressively smaller in the past 3 cycles. Right? Our space age, or not really space age started earlier, but our instrumentation to study the sun, that really came of age sometime around here, a little bit earlier than that, and we have now more and more impressive instrumentation which we are sending in space to look at the sun and understand it. So a lot of people are sort of unhappy that this is the time which sun is choosing to not show us much activity because the lifetime mission is typically 5-6 years, and in that time if you don't get many bursts or events or CMEs or whatever is it that you're looking at, you're not able to do the science which you are interested in. This last minima we had 100 days consecutively when we did not have a single sunspot on the sun. It was the quietest period in the past century. Okay? Now the sunspot cycle, not only is there a cycle in the number of sunspots which you see on the sun, there are other aspects to this cycle as well, and one of them is what is being shown here. So on the top panel, the x-axis is again time in years. The y-axis is the latitude at which a sunspot appears. Okay? So, and the bottom panel is what you have seen already, the average daily sunspot number. What this red line is trying to show by example is that this is the start of a new cycle. At the start of a new cycle, the sunspots appear at something like plus minus 30 degrees solar latitude. As the cycle progresses, the latitude at which these sunspots appear, it tends to migrate closer and closer to the equator. And at some point, these guys disappear from close to the equator and reappear again at plus minus 30 degrees latitude or so. And for obvious reasons, this diagram is called the butterfly diagram. Right? It was first made by a scientist by the name Carrington. It also therefore goes by the name Carrington diagram. Okay? So again, not only there is this number of sunspots which changes, it's also the position of these sunspots on the sun which changes. And that again, I am not going to get into that in this talk, but that is again related to the magnetic field, magnetic fields on the sun. Okay. There are many manifestations of this solar cycle. This is a bunch of X-ray images. There is one representative image from each year, and there is a total number of 11 images here, starting from chronologically, they are going like this. This is taken at the maxima of the solar cycle. The minima of the solar cycle is way back at the end. You see that we had earlier seen that these X-ray bright regions, they are always associated with the active regions on the sun, and you see a large number of them close to the maxima, and at the minima there is hardly any. This is from extreme UV. Okay, so extreme UV is now sensing a temperature which is order 10,000 Kelvin or so. That's the sort of temperature which is there in the chromosphere, which sits right on top of the photosphere. There again you see a lot of similarities with something like this, where you have a lot of structure in this emission close to the maxima, and the minima is basically a boring sun. There is no surface feature which you can see. This is something quite different. This is now, I said there is something called the solar wind. There is this plasma which is escaping from the sun all the time. What this plot is showing is the speed of this solar wind. Okay. Now the deep blues here are something like 750, 800 kilometers per second, and these reds in this equatorial belt are something like 300 kilometers per second. At the solar minima, it shows you a nice clean structure where there is an equatorial belt of slow wind, and there are big polar regions of very fast wind. This, and if you recall a picture which I had shown you earlier, where you were easily able to see the magnetic fields in the solar corona, that came from close to a solar minimum. That is a time when close to the poles there are open magnetic fields. These open magnetic fields are like channels along which this plasma can happily flow. There is there's nothing to constrain them. On the other hand, if I have a closed magnetic field, plasma is constrained to flow along the magnetic field. So it cannot therefore leave the sun and go away. So for those of you who have not had a course in plasma physics, it's good to think of highly ionized plasma and magnetic fields as beads on a wire. So the magnetic field is like the wire, and the plasma is like the bead. You can't move one without moving the other. Okay. So in the case of the sun here, where you have what we said was low beta plasma, where the magnetic field energy was dominating the plasma kinetic energy, the situation is like having a very stiff wire and a very light bead. So the bead has no control. A bead cannot drag the wire or anything. The wire is going to dictate what the bead is going to do. In the other instance, where the electron kinetic energy exceeds the magnetic energy, it is like the bead is very heavy, and this wire, or this rather than wire, you should call it a very flimsy thread, right? So the heavy bead can then decide the dynamics. If it is moving in some direction, it is going to drag that thread along with it. So that is what is happening in this region. It's actually not dragging it. It does not need to drag it. It's easy for this bead to flow along, to move along this wire, which is a straight open magnetic field line. And all the closed magnetic field lines are in this region around the equatorial belt. While things are very different when you're close to the maxima, where the whole surface seems to be covered by this slow solar wind, which suggests that the magnetic field configuration here must be pretty complicated. There are small closed loops of magnetic field all over the place and no open magnetic field. That is why it is something like this, or maybe really small patches of open magnetic field. This is exactly what is seen in this image as well. So this is what you had seen already. This is another picture of the sun taken at a solar eclipse, but this time close to solar maxima. Now this beautiful structure where you could have recognized a north and a south pole, etc., is simply not visible here. Right? There is no axis of symmetry which you can draw there. It just shows a lot of magnetic field all over the place, all sorts of structures, but no global magnetic field arrangement. Right? That is exactly the reason why this solar wind also looks like this. Okay. Okay, very good. Okay, something a little more about the solar wind. So its discovery, a lot of people attribute it to Biermann, but there was a paper by Paul Anhert just a couple of years earlier. Both of these guys noticed that whenever there is a comet which approaches the sun, there is a tail of the comet which is always pointing away from the sun. So the simple argument was that there must be something which is coming from the sun which is pushing this thing away from the sun. And that thing got known as solar wind. Okay. If you were to look at it now in a little more detail, you'll find that there are actually two tails. There is something called a gas tail and there is something called a dust tail. And there's a good explanation of what these are on the Wikipedia. So if you're really curious, take a look at that. There's one which goes radially out and one which goes in a spiral. And it's quite interesting to find out why. Okay. And a hint to the answer is here. So the sun we know is rotating. It's hard to say that it is rotating with a given period because sun is what is called a differentially rotating object. The equator is rotating faster, and as you move further away from the equator, the rate of rotation is slowing down actually. But if you were to just stick to the equator, the period of rotation is 27 days. Okay, one rotation in 27 days. And now from this sun, there is this solar wind which is flowing out. There is this heated plasma which is moving out at the equator at around 350, 400 kilometers per second, some number like that. And I said that this plasma and the magnetic field, they cannot be separated from each other, right? The plasma, the magnetic field which was threading a particular bundle of plasma, that magnetic field will always thread that bundle of plasma. It's a bead. The plasma is the bead and the magnetic field is the wire. I can't take this bead and put it on some other wire, right? Okay. That is what is being shown here. So what these lines are showing now, so there is sun at the center, and we are seeing from very high on the north pole of the sun in the ecliptic plane. And so the rotation of the sun is happening like this. What these, let's say, red lines are showing are the locus of all the points of all the plasma which has originated from one particular point on the sun. It's a little bit like the garden sprinkler, right? There's the garden sprinkler which is rotating and spewing out water, right? So once that water has been thrown out of the sprinkler, it is going to move in a straight line. And behind it, the sprinkler is going to turn a little bit and then throw out the next jet of water and so on and so forth. So what is happening is that if this was my sun and I want to track this place, so it has thrown out plasma in this direction. After some time t, this guy has moved here. In the meantime, the sun has rotated and this piece has come here. And now it has thrown out something else, and that has maybe reached here. But in the meantime, this guy has reached further out, right? So if I have to draw a trajectory of all the plasma which has come out from this place, I am going to end up drawing an Archimedean spiral. Okay, and how tightly wound that spiral is will depend on how fast this thing is moving. If it is moving very fast, the spiral will not be tightly wound. If it is moving much slower, the spiral will be more tightly wound, right? So this is basically what is being shown here, and that was what was first demonstrated by somebody by the name Eugene Parker. And just a couple of years downstream, there was actually a spacecraft which went up and actually measured the solar wind plasma, and that was really a phenomenal achievement to have observational verification of a very sort of heavyweight theoretical result so quickly. Okay. In reality, things are a little more complicated than this because you can think of the sun, especially when it is far away from the maxima, as having a dominantly northern polarity hemisphere and a dominantly southern polarity hemisphere. That the open magnetic field lines which are going to come out Most of them which are coming out from one hemisphere will be, say, going outwards, and from the other hemisphere they'll be coming inwards. And the demarcation between these two is something called a current sheet, or a magnetic neutral line. That neutral line, it so happens, is not just a line of a constant latitude or 0 degrees or something like that. It's sort of an undulating line. It moves up and down. And it is the projection of that line as this wind is propagating out is what is being shown here, right? So this is referred to as the ballerina skirt model of what the heliospheric current sheet is like. The projection of this magnetic neutral line as you take it further out is referred to as the heliospheric current sheet. Okay. Okay. This is another measurement of the solar wind in the heliosphere. This was done by a satellite by the name Ulysses, which was the first satellite which left the ecliptic plane. Ecliptic plane is the plane in which the Earth orbits the Sun. Most of the satellites which we have, they orbit the Earth actually. So naturally they are going to stay in the ecliptic plane. But we wanted to know what the solar wind is like when you go far away from that. We actually wanted to go do a full circle across the Sun in latitude. So cross the solar North Pole and the South Pole and all the intervening regions and see what it is like. So that is what this satellite managed to do for the first time. What this is showing you is actually a lot of interesting things here. So it's a sort of polar plot. The radial axis is the velocity or the speed of the solar wind. So this is 500 and this is 1000, and this is speed in kilometers per second. I hope you can make out a color. This is red and this is blue. So the color is showing you whether the magnetic field which was measured at that point, was it going outward or inward. So the outward magnetic field is red and the inward magnetic field is blue. So it is showing you that this hemisphere is dominated by that red and this hemisphere is dominated by the blue. Once you're away from the equatorial belt, this speed is more or less constant and sitting at something like maybe 800 kilometers per second. But while you are in this equatorial belt, the speeds are much lower, right? The 500 mark is somewhere here. So it's a little bit less than the 500 kilometers per second. And it's also very variable, right? As compared to something like this, which is pretty much steady at that particular value. This speed is much more variable. This is how the picture was at the solar minimum. They also had a corresponding track during solar maximum where it was very hard to look for such patterns. I don't have a copy of that here though. Yeah. Okay. Now just to round up our story of what all do we see on the Sun, what you hear most often about the Sun are something called coronal mass ejections, right? These days they often make it to the newspapers, and there is a spaceweather.com which will tell you in great detail about any of these events. What is happening here is that there is a lot of magnetic field which has been sort of twisted and tangled and has built up a lot of energy. You can also think of magnetic fields as a little bit like rubber bands. I can twist a rubber band and it builds up tension, and if I keep doing that, at some point it will break. Something similar or something analogous you can imagine happening for these magnetic fields as well. When the energy which has been put into these magnetic fields is extremely high, they look for ways to relaxing to a lower energy state, and sometimes those states come by ejecting a lot of the material away from the Sun. And when this happens, it is called a coronal mass ejection. Okay? And this tries to show that I had some movies which have disappeared, but I can show you a different movie in a little bit. These two images come from satellites which try to create artificial eclipses. So they are sitting at something called the L1 point, which is 1.5 million kilometers away from the Earth towards the Sun. So they are on the Earth-Sun line and sitting away from the Earth but looking at the Sun all the time. They have a disk in front of them which blocks the light from the Sun, and the rest of it is then just the reflected light, scattered light from these electrons in the corona. And when you have something like this, that is actually showing you this coronal mass ejection, that there is something which is very bright, which is reflecting a lot of light and is coming towards you. And because this is along the Earth-Sun line, if it is something which is coming towards us, it looks like a halo. it surrounds the sun on all sides, and so these are called halo CMEs. Okay, this is a cartoon to show the same thing. This is what a coronal mass ejection is. Depending on how fast it is traveling, it can take between 2 and 4 days to reach the Earth. Now, the key thing which I wanted to point out here is that this thing is a magnetic structure. Let's say this was a sort of magnetic structure, and this was the orientation of the magnetic field of this guy. And as it is going to come towards the Earth, this thing is going to move this way. And Earth has its own magnetic field, right? It has its magnetosphere, which is our sort of protective blanket. If the orientation of the Earth's magnetic field is parallel to this, as this guy comes and bumps against this, it is only going to sort of push it around it, but it is not going to be able to penetrate that, because these magnetic fields are oriented similarly and they are going to repel each other. And what is going to happen is that all this energetic plasma which would have come with this is going to compress this magnetosphere, but it is going to flow along the sides. And that is not such a disaster. If, however, this magnetic field was oriented differently, and if it was to propagate all the way from here to there, at this point it is going to find oppositely directed magnetic fields, and a process which goes by the name magnetic reconnection takes place, where under certain circumstances, when oppositely oriented magnetic field comes close to each other, it can achieve a lower energy configuration by reconnecting. And then a lot of the energetic plasma which this CME was bringing along can now travel along this new magnetic line path which has become available to it. At Earth, our magnetic field lines go to the poles. So that is where this energetic plasma is going to go. Okay? And that can have significant impacts on the Earth. And these are what are referred to as space weather impacts. So these range from, let's say, having enormous amounts of current running through the Earth's atmosphere, which in turn induce currents in the Earth's crust, which then can have catastrophic impact on, let's say, power grids. And in fact, people in northern Canada have lost power at least on 2 occasions because of something like this happening. Because something like this completely changes the structure of ionosphere and makes it very disturbed, all our satellites which are on the other side of the ionosphere, the communication with them gets disrupted, because this communication is via radio waves. These radio waves suffer propagation effects as they pass through this very turbulent plasma now, and we are, for example, no longer able to use the GPS, or a lot of other communication satellites get affected. Airlines, so if you had to go, let's say, from here to Boston, the shortest route is to go via close to the North Pole. That is the region where all these energetic electrons are going to come, so the airlines then don't flow through the shortest routes, or they try to avoid going through close to the poles. So these are some of the impacts of something like this. And a lot of the satellite, the most expensive thing is probably the damage to the satellites which take place, because they were never designed to swim in this pool of plasma. So we typically, for every big event, we lose typically 1 or 2 satellites. And it also happens that you now have much more materials, so the solar cells of these satellites, when they are impinged by these energetic particles, their energy efficiency drops by a couple of %. They experience a larger drag, which means their orbits are going to decay, they are going to fall, which means that if you want to bring it back to its orbit, you have to raise the orbit, which means that you're going to spend your fuel in doing that, so that reduces the lifetime of the satellite and so on. Yeah. Okay, so that was about the sun. I briefly also wanted to say something about the instrument which we have been using to study the sun in our particular case. It goes by the name of Murchison Widefield Array. This is an actual aerial photograph of the place, except these white squares have been put in Photoshop to show something about the telescope. But the terrain you see is the real terrain where this telescope is. Where exactly is it located and why? Well, it is in Western Australia. This is in the outback region of Western Australia. That's a place which is really very harsh to live. When you saw this picture, you saw that there's basically nothing. Okay, to give you a sense for scale, this square is 5 meters by 5 meters. Okay, and that is, this green is basically some shrubs and trees. They look much larger primarily because of the shadow. Okay, they are actually much smaller than what they appear in here. The reason why we are in this place, because this is, let's say, an area of about 41,000 square kilometers, and its population is 110 people. Okay. So that's a population density of something like 3 millihumans per square kilometer, which is something like, I think, 5 orders of magnitude lower than what we have in Pune. Actually, what we have for an average in Maharashtra, if you take it to Pune, I think it will be another order of magnitude at least. Okay. And the reason why we have to, it's a very hard place to live. The temperature in summer exceeds 50 degrees in shade. There's no water. When we had gone there to do the survey for this telescope, they told us that we can give you food, but please bring your own water. Okay. So the reason why we are going to such a harsh place to build this telescope is because we want to get away from people. Why we want to get away from people is because people use all sorts of things which create radio frequency interference, which is what I had spoken about with Kaushal in a previous talk. Right? So it is to go to a clean environment where we can actually study the cosmic signal without bothering about what is coming from terrestrial neighborhood, that we put in so much effort to go to such a hostile place to live in. It also has the world's largest density of poisonous snakes and insects. Okay. Okay. So this is another picture of that place. This is what one particular element of this telescope looks like. There are 128 of these. Each of these is a sort of 4x4 array of dipoles. There are some sorts of receptors which are gathering electromagnetic radiation. This is the frequency band it works in, 80 to 300 megahertz. These things are spread over a 3-kilometer area. Okay. Now, since the time I made this, we have now changed the configuration and we can now go up to 5 kilometers. But nothing much else changes. The time resolution with which we work is half a second. The frequency resolution with which we work is 40 kilohertz. And what this means is that every half a second we can make an image of the sky. And just like our eye can see many different spectral, many different colors, all the way from the violet to the other end of the spectrum, we can also divide the spectrum very finely, and in each channel of that spectrum we can make an independent image. And the reason why that is useful we'll see slightly later. So a little bit more about the telescope. This telescope has, I told you we have 128 elements. Most of them are there in a central dense cluster. This is actually an image of that cluster. And from there the signal goes to something we call a receiver. This is basically a big box of electronics which gathers data from 8 of these tiles. Each of these things we refer to as a tile. So these receivers gather data from 8 of these tiles, and then they send it out via underground optical fiber cables to some central processing facility. That is where there is significantly more processing done on these data. And from there, they are sent out to the city of Perth over 800 kilometers of optical fiber. Okay. And in Perth, they sit in this place called the POSI Supercomputing Center, which is where, for example, I log in to download the data and then work with these data. Okay. Okay. So now something a little bit more about the sort of nature of emission which we see from the sun and the corona. Okay, on this plot, on the x-axis we have frequency, and on the y-axis we have height above the solar surface. Okay, solar surface, whenever I say solar surface, I mean the photosphere, the visible disk of the sun, which you are talking about. And it shows 2 curves predominantly, which makes sense, or which would be easier to understand for those of you who are somewhat familiar with plasma physics. And I'll try to explain what they are. This curve, which is called nu p stands for plasma frequency. How many of you already know what is plasma frequency? Okay. So plasma frequency is the frequency that if I have electromagnetic radiation propagating through some medium, some plasma, if the frequency of my radiation is lower than my plasma frequency, that frequency will not be able to propagate through this medium. It will get absorbed. Okay. But if the frequency of my electromagnetic radiation is significantly higher than my plasma frequency, it will be able to penetrate through that. I'll be able to see it at the other end. Okay. So this is how plasma frequency is changing as a function of height in the in the corona. So that tells you that basically if I have to look at, let's say, let me go to this sort of light pink region, this marks the band of the instrument which I was talking about, the MWA, the Murchison Widefield array. I said we work from something like 80 to 300 megahertz, and that is roughly what is shown here. Actually, it should have been even smaller than this. Okay, so this tells you that, well, this is the frequency range which I am working. These are the heights from where I can see this radiation to be coming from. If this radiation was coming from any lower frequency, it will anyway not be able to escape from this medium because it will get absorbed by that plasma. It is only radiation at this frequency and higher which can actually come, which can escape from here, and I can see it. Okay? So this tells you that just by choosing the frequency at which I am looking at, I have some sort of a control over the height from where this radiation might be coming, or the greatest depth which I can see. There is another curve which is shown here, which is this one, which in this region at least they are quite close to each other. That is called the frequency where the free emission has an optical depth of unity. What is free emission? When you have plasma, you have essentially a bunch of electrons. When an electron is being scattered by another electron, it is being accelerated, and as any charged particle is accelerated, it is going to give out some electromagnetic radiation. The radiation which you receive from acceleration, from scattering of free electrons from other free electrons, is what is called free emission. Okay? And this tells you that when you, what has the ingredients which have gone into this are actually the density in the corona. That decides that when will a given medium become opaque to its own radiation. I am producing radiation because I have electrons which are scattering across each other, but if I put in too many of these electrons, all the radiation which I produce will also get absorbed by the other electrons in the medium. The place where this becomes a significant possibility, where 67% of the radiation which I produce actually gets absorbed by the medium itself, is given by this height. So these two are the most relevant things for us to understand in where the radiation which we receive in solar coronal physics is coming from. Okay, I was talking about a black body curve earlier. Here is an example of what a black body curve looks like. On the x-axis here is wavelength. This is the low energy end or the long wavelength end, and that's the high energy end. If you look at these numbers, right, this curve here corresponds to something like 10,000 Kelvin. Just below that, the red curve is what corresponds to the sun at about 6,000 Kelvin. And if it was just a black body at 6,000 Kelvin, that curve should have just continued like this. But what happens is that the sun has sitting on top of it corona which is at million Kelvin. Right? That million Kelvin plasma is also going to be emitting some radiation. Right? And because of that, this curve begins to deviate from what a black body at 6,000 Kelvin would be. That corona, however, is not unlike a black body which is perfectly opaque. It has an optical depth of infinity. Because it is not opaque, this curve has not jumped to the curve of a million Kelvin, at least not right away. Okay? So it has slowly begun to rise till the time it goes to frequencies where this medium has now become opaque to its own radiation. That is the tau free equals 1 which I was talking about. That is where it begins to approach a million Kelvin. Okay? In this region which marks the region which is studied by this particular telescope, we are in a region close to where it has become opaque. The corona has become almost opaque, and the temperatures which you see are close to a million Kelvin. Then you would notice two curves. There is something called the quiet sun here, and then there is something called the disturbed sun there. The disturbed sun is just to say that, well, this quiet sun emission is always going to come because there is always this corona. On top of this, we have all sorts of other phenomena which take place, which add much more emission to what is coming from the sun. And that, as you can see, it can raise the temperature from something close to a million to almost 10 billion Kelvin. When I say it is raising the temperature to 10 billion Kelvin, that's not the physical temperature of the thing. What I'm saying is that if I imagine a black body which is giving out so much radiation, the temperature of that black body would have to be 10 billion Kelvin. This radiation is not coming from a black body. This radiation is being produced by some other mechanism, and I'll say something about those mechanisms as we go forward. But it is as bright as a black body of 10 billion Kelvin would be. So it's a really very bright emission. Okay. Now, moving more towards what we want to study in the radio waves, this is what the sun looks like at different radio frequencies. If you were to go back to just a bit, or okay, maybe flip back and forth. This is 410 megahertz, which is close to 1 meter wavelength. 300 megahertz is exactly 1 meter, so this is like 75 centimeters. This is 5.7 gigahertz, and this is 17 gigahertz. Okay, and something like here or maybe even here, it seems more and more like the optical sun, which you are more used to, right? And that is pretty much the case, because at these frequencies where you're setting something like here, you are actually seeing just the solar black body. This million Kelvin plasma sitting on top of the sun is practically transparent at these very high frequencies. So you just don't see it, and you see just the surface of the sun, which is like the black body at 6000 Kelvin. But at this 410 megahertz or close to 75 centimeters, which is where you're sitting somewhere here, you are now seeing something which is much brighter, and now you are beginning to see the corona. So this, I hope you can see this faint circle which is marking the optical disk of the sun. You see emission coming from outside that, right? So that is where the corona is. So in fact, it is the emission from the corona which you are seeing, and that corona is already sufficiently dense that you don't even see the disk of the sun. You're only seeing a layer of the onion which is on top of the sun, and not the sun itself in some ways. Okay. Okay. So just a sec. So the right reason would be because the intensity of emission from the sun has changed well beyond, or has grown much larger than what it often is, or than what it normally is. Okay. And if you were to associate a temperature with that radiation, the temperature would be much larger than the temperature of the sun also. Okay. Okay. Now, there is a huge variety of emissions which come from the sun, and now I'm talking purely about radio waves here, which go in frequency from something like 3000 megahertz or 3 gigahertz to something like 10 megahertz. And on the x-axis here is time, on the y-axis here is frequency. So what something like this is telling you is what is the shape of this emission from the sun in a plot which has time versus frequency, right? So it's sort of telling you the morphology of this burst in the frequency time plane. And these got labeled as types 1, 2, 3, 4, 5, sort of in the order in which they were discovered. Okay, these starting 1950s, people have been working on these. And I don't want to really describe to you what these are and where they come from, except for just pointing out they have an enormous variety in shapes and strengths also. So these type 3s, which are labeled here as just vertical lines, right? They actually are drifting in frequency at the rate of something like few hundred megahertz per second. They start at a higher frequency and then they drift very quickly to lower frequencies, and the emission is moving in frequency. Then there are these type 2s which also show these drifts, but they are drifting at much slower rates. They are more like few tens of megahertz per second, and these often come in pairs, and these pairs are related to each other as harmonic pairs. So the lower frequency is usually the primary, is the primary, and the higher frequency is twice this frequency. Okay, so we know that they are related to each other by a fundamental and a harmonic. These are they last for a very long time, and then they fill up just a large part of the spectral space which is there, but they are much less bright as compared to these type 2s and type 3s. Type 2s are by far the brightest. They can give rise to tens of billions of Kelvin brightness temperature. These are they can still approach many tens or hundreds of millions of Kelvin, but they usually don't approach billions of Kelvin. So this is just to show you that all sorts of different kinds of emission can come from the sun. Here is now some data from the telescope which we have been working with. At the bottom here, it gives you the frequency at which this emission was observed. So it goes all the way from 80 to about 300. So it's basically 12 groups. Each group is something like this. It's around 2.5 megahertz wide, and between these 12 groups we span the entire range from 80 to 300 megahertz. And what I want you to notice is this, all sorts of structures which you see in here. Let's take a look at, say, something like this. Something bright happened here. It's only 5 minutes of data on the y-axis. Time resolution is half a second. Spectral resolution is 40 kilohertz. I can see it in this 116 megahertz band, but by the time I get to 100, I don't see it. By the time I am at 130, I again don't see it. Right? On the other hand, there are some other things where, yeah, it's bright here. It's also bright in the adjacent one and maybe in the previous one also. There seems to be a lot of structure which is which seems like fibers here. Right? These are fibers in across frequency. They are very short-lived in time, but maybe spread across frequency. Some of them are spread longer, some of them are spread shorter. Some frequencies tend to have many more of them, some other frequencies have very few of them. Right? So all sorts of structure is present in this solar emission. Okay? And this particular telescope is an imaging instrument. So for every pixel on this plot, I can actually make an image. And if I was to do it, I'll end up with almost 500,000 images with 5 minutes of data. So that's an enormous amount of data to deal with, enormous amount of processing to do. And after you've done these images, again, it's a big challenge to figure out what these images are actually telling you here. Okay. This is data from a different telescope in a somewhat different range. It goes from about 20 megahertz to about 90 megahertz. And again, it shows you a variety of emissions which are coming from these. This is time of about, I think, 2.5 minutes or something like that on the x-axis. And it shows you lots of things which are very short-lived, which just come and go. Some of them seem to drift. Some of them are just individual brightenings which take place and go away. If you look at it in polarized light, circularly polarized light, you know that light is polarized, right? There are two polarizations, two orthogonal polarizations of light. This one is about Stokes V, refers to the circular polarization. So some of the features which you see here, I'll go back and forth to help you identify. Some of them you can see as features in this polarized light, and some others, for example, these guys, they don't show any trace in polarized light. So some of this emission is polarized and some others is not. That again is a clue as to where the mechanism which is giving rise to this radiation. Okay. So now to come to the coronal heating problem, which is the thing which we were trying to study in this thing. The corona, like I said, is at about 1,000,000 Kelvin, and this has been known for almost 70 years now. And we also realize that the source of heat flux must be below the photosphere. Photosphere itself is at 5,800 Kelvin, and we know that thermodynamics prohibits flow of heat from a colder body to a hotter body, right? So conduction, convection, radiation is not going to get you the heat from the photosphere to the corona. So you must find some other way of doing it. People have, of course, been able to calculate how much heat flux do you need, because we know a lot about the corona. We know its temperature, we know its density, we know at what rate will it lose energy if we just were to heat it and let it be, because it's going to radiate away all this energy. So you can find out at what rate must you supply this energy to keep it at 1,000,000 Kelvin, to sustain the temperature at 1,000,000 Kelvin, and that's a pretty large rate, 10 to the power 4 watts per meter square. And that again we've known for a very long time. What we have also now known for almost 30 years is that the magnetic fields in the corona, they have sufficient energy to be able to act as the reservoir from where to draw this energy to heat up this corona. Okay. So all of this is now turning out to be a problem of how to extract the energy from the magnetic fields and use it to heat up the corona. That is really what it is about. Our problem basically is that we have not been able to find the observational evidence for this heat flux. We know our magnetic field has energy. We have not been able to figure out how is this energy being taken out and being put into heat. Now, the layer just below the corona is what is called the chromosphere. Chromosphere requires even more energy to heat, because even though it's at significantly lower temperature, it is much, much denser as compared to the corona. So the amount of heat required, amount of energy required to heat it up even to the lower temperature is actually larger than what we need for the corona. So just for you to know, chromospheric heating is even a larger problem in terms of the heat budgets. Okay. So what are the various possible resolutions for this which people have been looking at? Well, there are two major contenders for how this can be done. One is called wave-based heating. It's also known as continuous heating. And basically the idea is the following. We know that our sun is full of magnetic field. We know that there is a lot of convective motion which is taking place at the base of the photosphere. And this convective motion is jiggling the magnetic fields around, right? So if somehow I can set up waves in my magnetic field, waves are a very good way of transporting energy. So these waves can transport this energy further out, and then if I can get them to dissipate, I would have transferred this energy from the base of the photosphere to wherever I can get them to dissipate, right? So that is the idea. And so for the past many decades now, we have had more and more sophisticated instruments which have observationally been trying to look for the presence of these waves and their dissipation. And actually in the past decade or so, we have seen these so-called Alphen waves. Alphen waves are the waves in the magnetic fields, and we have experimental evidence for detection of these waves in a diverse variety of conditions on the sun. The problem, however, still remains. The problem comes from two reasons. One is that even in the region where corona is already hot, we can still detect Alphen waves. So if you are able to detect an Alphen wave there, that means that the wave has not yet really given up its energy, but the medium is already hot. Okay? So therefore it must have been heated up by something else, not by this wave which you are able to see there. The other thing is that even theoretically people are finding it very hard to come up with mechanisms which are going to dissipate these Alphen waves in the coronal conditions which are known to be. So it is really hard to take this energy out of these magnetic waves in magnetic fields which people have managed to set up. Okay? Though we do have evidence for the presence of these waves, we don't have evidence that these waves are actually giving up their energy to heat up the corona. The other hypothesis is referred to as the nanoflare based heating or impulsive heating. This was suggested by Eugene Parker, the same guy who did the first theoretical calculations about the solar wind in 1958. Right? 30 years later, he gave a phenomenal theory or phenomenal hypothesis for explaining coronal heating. Now, this was based on observational evidence from X-rays and extreme UV data that there is a large number of bursts which take place. Each of these bursts is regarded as some sort of a transient event, and we know that it is evidence for deposition of large amounts of heat in the corona, because that is the reason why it is emitting X-ray and EUV. X-rays and EUVs are sensitive to plasma at tens of millions of Kelvin or up to tens of millions of Kelvin. So something has impulsively heated this thing to this very high temperature. So what he said was that, well, imagine a carpet of these events, very large number of them, each one of them individually too small to be detected, but between this carpet you can deposit a lot of energy into the corona, right? It's like saying that it's Diwali night and I can hear the constant rumble of crackers, but I cannot identify individual crackers in there, right? It's some sort of a scenario like that. And each of these nanoflares is powered by a magnetic reconnection event. So, okay. I think this is saying the same thing which I already said, that he hypothesized the presence of a large number of weak events extending to ranges which are below our current detection thresholds. And things with an energy of something like 27 ergs per second were already named microflares by then. And he said, okay, let's go 3 orders of magnitude deeper. These ones we know you can't detect. So he called them nanoflares and said that if I postulate the presence of a large number of that at a mean energy density of about 10 to the power 24 ergs per second, then I need something like 10 to the power 5, 100,000 of them to be taking place at any given time to meet the coronal heating requirements. And since then, we've been building, we as in the grand community has been building more and more sensitive instrumentation to be able to push our detection ranges, detection thresholds to weaker and weaker energies so that we can see. Now, one very interesting thing to note here is that for a theory like coronal heating, nanoflare based coronal heating to be the right theory, you can actually theoretically show that the distribution function of these flares must have a slope which is smaller than -2. Okay. So therefore, now there is a discriminant. Now you know that the distribution function of the events which I detect must meet this criteria for them to be useful for nanoflare based heating. Okay, this was supposed to be an animated GIF. What it is trying to show is that the plasma is moving in along these directions of these yellow arrows, and as it comes closer, the reds and the blues lines are showing you the red is originally coming from top, the blue is originally coming from bottom, and at this point they will reconnect and then they'll begin to flow out. And so the red is going to connect to the blue, and that is how it is going to go. Let me see if I can. Nope. Can't seem to get this to work. Okay. Okay, so this is the basic idea behind magnetic reconnection, and taken in isolation. I'm not telling you anything about what is causing this to happen and so on, but this is what magnetic reconnection is about. Okay, so what is the current status of these nanoflare based coronal heating theories? So, like I was saying, that the bulk of the effort has been concentrated on studying X-rays and extreme UV events. That was natural because Parker's own hypothesis was based on observational evidence from X-rays and UV. Those were the places where the instrumentation has been steadily developing in the past few decades, and so that is where people had been investing all of their energies to find out what is happening. Now we are actually able to detect what was 3 orders of magnitude below detection threshold when Parker proposed this theory, right? So 10 to the power 24 ergs we are now able to detect. Our time resolutions are still a little coarse, but this much energy we can get to. What we have been finding is the following, that even the weakest X-ray features which we are observing, they don't meet the requirement for coronal heating. They don't meet, for one thing, they don't have the right slope. Their slope is shallower. The slope tends to be around -1.8. And there have been numerous observations by different satellites, different groups analyzing the same data and so on. All of them come to about the same number, -1.8. The other reason is that the distribution of these microflares or nanoflares seems to follow the distribution of active regions. Like I told you earlier, the active regions are available only between ±30 degrees latitude and lower. But the corona is hot even at the poles. So if this thing is following the distribution of the active regions, then it is not going to be the one responsible for coronal heating. Right? So for these two reasons, we know that even the weakest X-ray features which we have looked at are not the ones which are causing coronal heating. Things are not as clear about EUV, but much of what I said still holds. That is because EUV studies started a little bit later, and statistically one has to do a lot more work before you can get to just as robust conclusions as what you have at X-rays. This is some sort of a compilation of what people have managed to do. This is flare energies. You can see it is getting down to 10 to the power 4 ergs, and these are the slopes which people have managed to measure. These are the weakest ones for which we have good robust slopes, and this number sits at -1.79. Right? This one is -1.74. Okay, so I wanted to say just something a little bit more about the basic reconnection scenario as it applies to radio waves. What are we interested in and why? So we are also, what happens in a magnetic reconnection? Now this is a cartoon which has the surface of the sun here. These are some of the magnetic loops which you saw coming out of the sun. For some reason, this loop which is here is being pushed, right? It is being sort of pushed towards each other, this opposite polarity of magnetic fields. And that is where a so-called X-shaped magnetic reconnection is going to take place. Now the magnetic energy which disappears here is going to be used to heat up this plasma. This plasma, again, as you know, is confined to travel along the magnetic fields line. So some of this plasma is going to flow down. As this plasma flowed down, it hit the dense surface of the sun and it was suddenly decelerated, and that is where the Bremsstrahlung radiation, which was giving rise to the X-rays and EUVs, was being produced. That is what all the studies which we were talking about earlier were using. It also happens, however, that some of this plasma also flows along the magnetic field lines which are open and going up. Those magnetic field lines give rise to radio emission. Okay. So the radio plasma is basically, these are the same electrons which are accelerated at this reconnection site, but they are now going up. Now because these are hotter electrons, as they move in an ambient plasma, the hotter electrons are going to be able to move faster than the colder electrons which are in the neighborhood. They give rise to something called bump in the tail in the velocity distribution. Now that's an unstable distribution, and you can show that via some detailed plasma physics that this unstable distribution is going to decay via a coherent emission process. That coherent emission process is going to produce electromagnetic radiation at the local plasma frequency and its harmonic. Okay. And it so happens for us that the telescope which we are using, we sit at the right range where the frequencies in which we observe correspond to the plasma frequencies in the region from about half a solar radii to about 1.5 solar radii above the sun. So if these electron beams, they are propagating in this region, then the coherent emission which is being produced from them we will be able to see. Okay. So what is the big advantage? The big advantage is the same thing as what this laser offers, right? It is using a microwatt, but the spot it produces on that wall you can see from very far away. Why? Because the radiation which is emitting, is coherent. Exactly the same thing is happening here. So this radio waves which are coming out from here are coherent emission. Even though the energies which are associated with them can be very small, the observational signature they produce can be very large. That is why we saw things which were producing something like 10 billion Kelvin of observational signature. That was just the temperature of the radiation, not physical temperature of the body which is giving rise to it, right? So what we can find is that even the weakest of flares, weakest of electromagnetic impulsive signatures which we see here, they are often 10 to the power 8 Kelvin, 10 to the power 9 Kelvin. And however, if you have to produce that sort of a thermal signature, you need really a lot of plasma to be heated up before it is going to show up as something that hot. Okay. So these coherent emission implies that very small energies can give rise to very large observational signatures, and that is the strength of the work which we are interested in. Okay. So now, after a long and rambling preamble, I am ready to talk to you about what exactly we did, right? So the questions we wanted to ask in this particular context are the following. I said that there is this million Kelvin plasma. This million Kelvin plasma is going to produce some free radiation, right? It will have electrons which are scattering off each other and are going to give rise to electromagnetic radiation. Now this radiation, because this plasma is this huge body, right? That will be slowly varying in time, because that corona cannot vary quickly in time. It's a huge elephant. It can't move fast. It can't change quickly. And it's also going to be spectrally smooth. It can't have features which have peaks in the spectrum, because free scattering has a very smooth spectrum. And you can show by a little bit of analysis that if you were to look at the distribution of radiation which is arising out of this million Kelvin free emission, it must follow a Gaussian distribution. You can rigorously show that this must be the case. On the other hand, if you have all these weak reconnection events, which are impulsive in nature, right, which they just happen and go away. The first question we wanted to ask is that can we separate these two in the data which we are looking at, and if we can, then what can we say about the characteristics of the slowly varying and impulsive emission? Because we believe now that the slowly varying emission must come from the thermal, or it must be dominated by the thermal emission or the free emission from the corona, and the impulsive emission must come from these magnetic reconnection like events. So that is the basic model which we are trying to make. And this work was published earlier this year. Here is a reference in case you are interested in following up in more detail. So this figure, sorry, the time axis got cut. On the x-axis is time, 1 hour of data. On the y-axis, these numbers give you the frequency at which this radiation was observed, which goes from something like 108 to about 240 megahertz. There is about 2.5 megahertz at each block. The color tells you the strength of this emission. This SFU stands for solar flux units. Okay. A solar flux unit is 10 to the power 4 Jansky, just in case somebody is familiar with the unit which radio astronomers like to use for flux. Otherwise, SFU is pretty good, solar flux unit. So you see that at lower frequencies, maybe the flux is something like a couple of SFU. At higher frequencies, it goes to something like maybe 25, 30 solar flux units. That is how things are changing, but at each frequency, you see these small vertical things, right? Again, the same fibers of emission which I was pointing out earlier. These are our impulsive emissions, which we always tend to see, and this is what we want to separate out from the rest of the emission. So this is just another view of the same dynamic spectrum which I showed you. To separate out this slowly varying component from the impulsive emission, we just used a median filter of length 1 minute. Okay, there's 1 hour of data here. We just passed a median filter through that, and this is what the median filter turns out to be. Okay. So you're just take 1 minute worth of data, look at the median value for that, plant it in this figure, move to the next sample, take the minute alongside around that now, take the median value, and that becomes the next time slice here, and so on. Now once you subtract the median filter from this original data, this is what you are left with. So now we are claiming that we have removed the slowly varying emission, right? Whatever was sort of steady on the time scale of a minute has now been taken out. Whatever was impulsive, whatever was varying significantly faster than that, is all that remains. And that you can see now that this thing is, most of things here are sitting at around 0, which is what should be the case if you have removed all the background on which this thing is sitting. And these peaks are at just plus minus 2, just to show you that there is actually a lot of structure, a lot of emission which is impulsive in nature, which looks like vertical lines here, which is present here. Okay. And just to show you the sort of correspondence, it's the same data as before, just sitting right next to each other so that you can see all of it together. Right? Okay. Okay. So now what we did next is that we took this data. For every frequency band, we did that separately. For any given frequency band, you just look at the histogram of what it is like. So now we are claiming that across this tiny bandwidth, this about 2 megahertz worth of bandwidth, we say that that's really too small for the corona to change significantly in its character, for this emission to change significantly in its character. So it can reasonably be described by a single Gaussian. Okay. What we are now trying to look at is this histogram of all the intensity values in each of these bins. So this plot comes from the data at 160 megahertz, which is this guy. Okay. So the y-axis here is on log scale, the x-axis is linear, and this is what it looks like. Right. So the black dots are the data. The various Gaussian components which were fitted to this are these dashed lines, and their summation is this solid orange line. Right. So that you can now see, convince yourself that the sum of these Gaussians is pretty good description of what these data are. I'm not sure if you can read the numbers from back there. There are essentially 3 quantities which are defining each of these Gaussian components of the model. There is the mean, which we are calling mu. There is the sigma corresponding to that Gaussian, and then there is the weight, right? The weight is the quantity which is defined such that sum of weight of all the Gaussians must equal 1, right? So weight is telling you what fraction of this data belongs to this particular Gaussian component. Okay. So this we did for all the various frequencies which were available to us. So there's a total of 9 of them, and that is what we did. So these are sort of in the order of lowest frequency to highest frequency, and the x and y axes are the same, and they are the same as this plot. So some things you are quite apparent already, that this seems most sharply peaked. The lowest frequency, which is coming from the highest heights in the corona, is the guy which is most sharply peaked as compared to the highest frequency which is coming from the lowest heights in the corona. Okay. There are what we found, for example, is this particular plot shows mu, the mean of the Gaussian, and because what we are most interested in really is the very first Gaussian. That is the Gaussian which to us corresponds to the emission coming from the thermal slowly varying component. That is really the only one for which we have any justification to claim that this must be a Gaussian. For the rest of it, we have no justification to claim that these are Gaussians, except that a Gaussian mixture model is such a general model that it is worth trying to see if it is able to describe these data or not. And what we find is that typically by using about 7 or 8 Gaussian components, that's enough to describe something like this. And the objective of our study is to find out how much data lives inside this very first Gaussian and how much lives outside that in the sum of everything else. That is what is helping us discriminate between what is coming from the slowly varying part and then what is coming from the impulsive parts. Okay. So everything here, this green component onwards, is what is sitting in the impulsive part. Whatever is sitting close to 0 mean is now what is coming from the slowly varying thermal component. Okay. So this first panel here has frequency on the x-axis, and on the y-axis it has the mean of the very first Gaussian, which I'm going to call mu1. I'm sorry you can't probably read it from there. This range goes from 0.0 to 0.1 in units of SFU. But the point to be noted here essentially is that the mean of the first Gaussian is less than 1% of the mean of the slowly varying component at that frequency. So to a very large extent, it has basically removed that slowly varying component by that median filter. Okay. So that is what we wanted to do. We wanted to move the slowly varying part out and then look at what the impulsive things are. And there are 6 points corresponding to each frequency here, because we used 6 independent data sets so that we can verify if what we are getting, how consistent are the results across different data sets which are looking at the sun at the same time. It is the same time, same frequency, but an independent measurement. That's because of the way the telescope is constructed. It allows us to make many independent measurements like this, but we restricted ourselves to 6 of them. The second set, if you can use the label here, this corresponds to sigma. The width of the Gaussian, what I'll call the first Gaussian, sigma 1, which is the one which corresponds to the slowly varying or the thermal component. There again it shows consistency between all the 6 sets, and it shows that as frequency increases, this guy also tends to increase. I did not point that earlier, but you can see that. Not only this is the most narrow and most sort of compact Gaussian here. As you come here, the Gaussian falls down in peak and it becomes broader. That's the same trend which you are seeing here. It is just showing consistency across different independent measurements. This one is really the quantity of interest. This is W1, the weight of the first Gaussian. What fraction of the data sits inside that thermal emission, right? This is, think of it in terms of what I like to call fractional occupancy in the frequency time plane. How many pixels in that dynamic spectrum, which had frequency on one axis, time on the other axis, and intensity as the colors, how many pixels, what fraction of the pixels in that data correspond to slowly varying emission? That is what is being answered here. Okay, so this goes from 1 to 0 here, and this is between 0.8 here and 0.4 here. So what it is showing you is that these data which we looked at actually, which comes from fairly moderately quiet times, almost half the data sometimes, right, somewhere between 50 and 20% of the emission is outside the thermal Gaussian. Okay. So there is so much impulsive emission happening even when nobody else seems to be seeing any signs of any activity on the sun. Okay. And of course, the point of this plot was to show that that this technique is successful at quantifying the slowly varying fraction of these data. Okay. Another result which we managed to get from this is shown here. Again, the x-axis is frequency and the y-axis is flux in solar flux units. The green corresponds to the flux of the slowly varying component, while this blue corresponds to the flux of the impulsive component. So that is essentially the mean of the flux in all the Gaussians except for the first one. Okay. So now if you were to compare that, this was really surprising for us that this green and blue are very similar in magnitude all across this spectral range, right? So the strength of the impulsive and the slowly varying emissions are very similar, even in moderately quiet times. Okay. This was absolutely unexpected and has not been reported by anyone earlier either. Now I had mentioned to you that a very interesting discriminant of whether something which you are seeing has anything to do with coronal heating or not is to look at the slope of the distribution function. So we tried to do that as well, and here are for some particular frequencies 109, 162 and 240 the slopes which have been fit to these. Now what we find is that these slopes are in the vicinity of well, minus 1.83, minus 1.69 and minus 2.35. But what we find is that our data is not actually, we don't have sufficient data to draw any robust conclusions. If we just change the limits across which we are fitting the slope slightly, and you can see that most prominently in the red one here, right? You see that there is a dip here and also a dip here. If I change the region where I fit the slope slightly, I get a different answer. So I just don't have sufficient data to be able to answer this well just yet, because here we are sitting in a region which is here, right? That is where I'm trying to fit the slope to find out what is the slope here, and this axis I have to turn into log. By the time I'm here, I have lost 2 orders of magnitude in terms of data as compared to the peak. So I really need to put together a lot more data in terms of sheer volumes before I can hope to answer this question or get a more robust answer to whatever this is, right? So at the moment we can't say anything more than, yeah, this looks interesting, but we have to do more work here. Okay. Now, as you know, that Gaussians don't form an orthonormal basis, right? So whenever you are dealing with a study like this, you must pay good attention to finding out if there are degeneracies or non-uniquenesses, or estimate the uncertainty in the work which you have done, uncertainty in the estimates of your Gaussian model. So that is what we tried to do, and that is what is demonstrated here. So the way we went about that was to say that, okay, when we give an initial guess for our model, we'll choose the initial guesses from basically a uniform distribution across the entire valid range for that data. So this one shows you the mu1 versus W1 plane and the distribution of the initial guesses. This one shows mu1 versus sigma 1 squared. Okay, and it shows essentially that we used uniform distribution across these 2 parameters to seed our initial guesses, and there are 1,000 points on each of these plots. So we did 1,000 simulations or 1,000 different attempts to run the Gaussian model, each time from a different seed or initial guess here. And this is the result of what we found. So now this is again mu1 versus W1 plane, and this is mu1 versus sigma 1 plane. This is for one particular frequency, 121 megahertz, the same plots for a different higher frequency and for yet another frequency. What these are showing you now, the blue points which you can see, or the scatter diagram which you can see there, those were the initial guesses. The guesses to which we converged are shown by these black dots which are there, right? And everywhere you will find some set of black dots. So that is initial guess versus the black dot. The color is telling you that this particular initial guess, let's say somewhere here, correspond to a final value with whatever is the color in the color bar. Okay. So that basically we wanted to see if there is a pattern there, that if you start from one particular part in the phase space, do you always reach some particular minima as opposed to some other minima, right? Just to get a sense for what is the nature of this chi-squared minimization hypersurface in which you are operating, that is there a preponderance or is there a tendency for some initial values to lead to some final values and some other initial values to lead to a different set of final values. That does not seem to be the case. You always find these colors to be very similar, so all these values are sort of converging here, all these values starting, no matter where you start from, are converging here, and so on and so forth. So that was very satisfying to see. Another view of the same thing is here, right? So this panel shows you the initial guess for W1, and this shows you the final value of W1 which was arrived at, and similarly the initial guess for sigma 1 and the final value of W1. In this plot you don't get a sense for how much data is sitting where. It just shows you that this was the distribution of your final values. By looking at this histogram, it tells you how sharply peaked that distribution was, right? So it tells you that how well constrained in that sense your final value was. And so we always find that the final values which we come to are really very sharply, very nicely constrained. The worst case scenario is what we have here, where we have, this is the only case where we seem to have significant number of points and a different peak as well, but the vast majority of them still sit in a single peak, and the distance between these two is not very much. Okay. Now another thing which you can do is that, well, this is what was one realization of the data. What if I had a different realization of the data, right? In some ways we already have it, in the sense that we have 6 independent realizations, which are 6 different independent measurements which we have been using all along. But we did something a bit more as well. What we did is that the same data we divided into 2 subsets by taking just every alternate sample. So we said that, okay, every even sample forms set A, every odd sample forms set B, and we subjected them individually to the same analysis. And what we find is that as long as we are dealing with Gaussians which have a weight of larger than 1%, right? So at least 1% of the data sits in that particular Gaussian component. The values of the weight, the sigma and the mu were always within 1% of one another. Okay. Only if you go down to a Gaussian which does not even have 1% of the data did these values differ by larger than 1%. That was also pretty satisfying to see that it's a pretty robust way of estimating this. Just to show you that this is not how it always is, this is some other piece of data, and this is what the dynamic spectrum looks like for that. So there is a complete absence of any of those what I was calling fibers of emission. If you were to do the same median filter analysis and look at the departures from that, subtract the median filter, this is what it looks like. If you were to do a Gaussian fit, this is what the Gaussian model representation, this is what the Gaussian mixture model looks like. Every time it finds just one Gaussian. Okay? And if you were to compare the widths, the sigmas of those Gaussian, the earlier data which I was showing you is in blue here, and these data are in red here. The sigmas of the earlier Gaussians were much larger typically than these ones here. That's just to show you that the sun is not always the same, that it has a lot of tricks up its sleeve. Okay? So that's essentially all I wanted to say. So let me give you the conclusions from this part, that the Gaussian mixture model, it seems like a pretty robust way for quantifying weak impulsive solar emissions, which this study actually managed to do for the first time. And at about 0.1 solar flux units, these are the weakest non-thermal solar emissions which have been reported at these frequencies. They are weakest by almost an order of magnitude. The earlier reports of weaker features are about an SFU or so. Okay? And physics-wise, it was really surprising to learn that even during moderately quiet times, something like 50 to 20% of this emission is coming from the impulsive part, or is the fractional occupancy of this impulsive emission can be as large as 50 to 20%, even though all other instrumentation in X-ray, EUV thinks that nothing much is happening on the sun. And also surprisingly, that the strength of this impulsive and slowly varying emissions are very comparable. I also wanted to take a few minutes to sort of advertise a project which I had, as I had said in the outline of my talk. So if there are no questions at this point, I can take a few minutes to talk about that. Of course, I'll be around for a few minutes more after that. So if you have any questions, we can chat about it then as well. Okay. So what I was looking for is, rather than calling AI, maybe I should have said ML, machine learning applications. That would have been a better way to say that. Machine learning applications to solar radio imaging. So like I was telling you a bit earlier, this particular instrument, the Murchison Widefield array, we can generate about 500,000 images every 5 minutes, right? And it's impossible for the human brain to wrap around whatever these images are telling you. So you must use some sort of an algorithm technique to extract the information from this and figure out how to make use of it somehow, right? So these images, it's best to think of it as essentially a 4-dimensional array. The various dimensions in this array are, because it's an image and it's an image of the sky, so just like a map of the earth, with every point on the earth you can associate a latitude and a longitude. Similarly, you can associate two angles, right? In astronomy, we call them right ascension and declination, with every point on the image of the sky. And of course, for every time slice, I can make an image. So there is a third axis, which is time. And of course, for every time slice, I have a large number of spectral slices for which I can make an image. And therefore, the fourth axis is frequency. Okay. So if I'm talking about, let's say, a 5-minute observation, so then I would have an array which is 600 units long along this axis. Along the frequency axis, I typically have 768 spectral channels. So that would be the number along this. And number along these theta and phi would typically be 100. So you can think of 100 by 100 by many hundred by many hundred array is what you are dealing with. Okay. The sorts of things which I was showing you earlier, the spectra, they are referred to as the dynamic spectra. And there what had been done was that the two angular coordinates, they had been summed up to say that I am interested in the emission from the whole of the sun. So irrespective of where it is coming from the sun, I am going to count it. So I am just going to not average, but sum up the emission from the whole sun. So those two coordinates, those two axes or those two degrees of freedom were summed over, and therefore no longer in the picture, and therefore you had only time and frequency, which is what I was showing you. Okay. To give you a sense for slightly different sort of data which we dealt with, this is again data from the same telescope. This is time on this axis, this is frequency on this axis, except that this is like 30 megahertz now on this axis. What each of these and green dots is telling you is that along with a student by the name Akshay Suresh, who was from ICER and did his master's thesis with me, we developed a wavelet-based approach for characterizing the features which we see in these data. The brighter features you can see here, but if I was to change this color scale from 0 to 120 to something like 0 to 10, you find many more features appear here. Okay? So each of these green dots has actually identified a feature in the spectrum which has sort of gone up and come down. Okay? And we used a Ricker mother wavelet to come up with our methodology to identify these. And we find an enormous, because it's interesting to look at what the slope of their distribution function is like. We did that, and these are the peak flux densities, and the slope is again minus 2.2, but you can see that we are limited by the data on either end. We are beginning to flatten out here, and we don't have sufficient data to look, we don't sample many high flux events here. But we found something like 14,000 of these features in just 4.5 hours of data. Okay. And again, the strength of these features we found were comparable to the weakest features which had been reported in the literature by that time. Now, the questions which you want to answer, these again, like I was saying earlier, have been integrated over the sun. Right? There is no information of where these things are on the sun. For that, you have to make an image. That is the question we now want to answer. Where are they coming from on the sun? is their distribution compatible with what you need it to be for them to be useful for coronal heating, right? Do we see anything happening close to the poles ever, right? Do they show any trends as a function of maybe time or frequency in where they are happening, their locations, or maybe their sizes and morphologies, right? What we often find is that these emissions, they are fit well by Gaussian like things. Okay, a two-dimensional elliptical Gaussian is a very good fit, very good model to describe these. So is the size of the Gaussian changing? Is its position changing? Is its position angle changing? Okay. We also have observations of the sun in a whole host of other frequencies, and from from X-rays to EUV and so on, and higher radio frequencies. Are there any associations of the features which we see with features seen in any other frequencies? And those would be both spatial and temporal associations. Do they always occur close to active regions like we see at soft X-rays and EUV, in which case we are still not yet at the things which are useful for coronal heating? There are a weaker class of events which are called jets and plumes, which seem to be coming from even places where we don't always have active regions identified. So far we can only see them when they happen on the limb of the sun, because when they happen on the disk of the sun, our instruments don't have sufficient contrast to be able to pick them up. Could they be associated with any of those, right? So these are sort of some of the questions which I just wanted to mention to you. I'm having some trouble embedding movies in this, so I wanted to play it from outside. Okay, so I hope you can see some things changing there. So each frame here is half a second. From this frame all the way to this frame, there are 48 different spectral channels which have been imaged. Out of the 768 channels which I have, 48 of them I am showing here. And you can see, okay, I'm not sure if you can see a whole lot here apart from maybe the flickering of these light sources. There is actually a faint disk here. That is the disk of the sun. Sitting on top of that disk are these things which sort of come and go. These are the lowest frequencies, these are the highest frequencies, even though they are only 30 megahertz apart. Oops. Okay, just play it one more time, and you see that these structures don't live across the whole 30 megahertz, right? The brightenings at different frequencies which come at different times. In this particular data set, much of the action seems to be happening at the same place. So clearly these are not the guys which are useful for coronal heating. But again, no one has managed to study these things at this level of detail. One of the most interesting things which we have managed to do with this instrument is to build a pipeline which gives us the highest quality images which people have managed to make of the radio sun so far. So our dynamic range, which is basically about what is the faintest object which you can see in presence of something bright. The dynamic range of the images which we are making are at least an order of magnitude, often 2 orders of magnitude better than what people have managed to make till now. There is another movie which maybe I can play, which shows the same data in a different format. Now each pixel here, okay, let me first draw something here. So you had something like the sun, and each pixel here was showing you a moving window in time and frequency. It was showing you actually 10 seconds of data, and I've forgotten now exactly how much I put in bandwidth, but it is showing you a little bit of past, a little bit of future, and a little bit of what is happening in the neighboring frequencies at the location from where it is coming. That is what it looks like. Again, it looks like that the bulk of the action is happening here, and there is the reason why you see very similar pattern appear everywhere here, even where there is no sun, that is because of the limitation in the dynamic range. This, I should have pointed out that the scale here is actually a log scale. So when it goes from 0 to 3, it is 3 orders of magnitude in difference. So that is why even though something is not happening close to where that bright thing happens, the noise even in very far away part of the image changes because this thing has suddenly become brighter by a factor of 1000 here. Okay. Okay. So basically we want to look for or discover patterns in this and find efficient ways to describe them. That is the heart of the problem. These could be like look for presence of clusters or local peaks or correlations in these various things. And for that, I want to explore the use of machine learning tools. And that is a project for which I'm looking for a student who might be interested to work on that. Thank you so much. Yeah. Thanks. Yeah.